in typical cases, when you're working on the final exam or midterm exam, the hardest or the most challenging thing you might find is how to find the correct note, how to find that correct topic we discussed in class, how to make that connection between an exam question and a topic we talk about in class. So my recommendation there is say, hey, the more familiar you are with the materials, the faster you can make that link. It will not work if you're reading the lecture note like line by line during the exam. You won't have enough time. So for the discussion worksheet, you worked on it once. You should be able to know how to do it. But then in order to get you familiarized with the material again, I highly recommend you take that discussion worksheet problems into a huge document and randomize the order in the process. And after randomize the process, go back and redo those problems again and see if you're really familiar with the concept and know which lecture note you should be referring to when you see that type of question in the exam. All right, so that's the first piece of advice I have. Second piece of advice is I posted my previous year's final exam on Canvas. You can see what to expect. It's going to be similarly 8 problems. The first problem being like 8 short answer, quick answer question. And then the second problem is going to be explanatory question, like why do we have 3p orbitals? Why do we have 5d orbitals? So those are the first 2 questions. The rest of the final exam will be 6 comprehensive problems that requires you to use different domain of knowledge in the class. So when working on the practice final, I highly recommend you do it on a timed fashion, because in the real exam you will be timed. And make sure you leave yourself a good 10 minutes, 15 minutes to submit your exam onto Grayscope, because you don't want to risk the late penalty. So that's the 2 advices. The third piece of advice is don't hesitate to ask for help, work with your friend. I mean, the moment you're talking to your friend, explaining a concept to your classmate, that also helps your own understanding. So working groups, like don't cry along in your dormitory. So those are the 3 pieces of the more general advices I have for you to prepare for the final exam. And questions about the final? We'll have more of this discussion on Friday, if given I have the time. All right. So today we'll go into our last chapter of our entire quarter, which is spectroscopy. We'll only touch on the surface of spectroscopy, and you'll work with Dr. Barr in 20B to look into more details about spectroscopy next quarter, assuming you're taking 20B though. And the Cengage assignment for the spectroscopy topic is not graded. It means it will not count for your final exam. I hope you have more time working on your final exam and not to be distracted by that Cengage assignment. So just so you know, this part of the Cengage is not graded. The last graded Cengage assignment is on the transition metal topic. Today, we'll be talking about 3 topics again. The first one is we'll look at how to decompose, the decomposition of molecular motions, and how do we describe energy in molecules, right? So we talk about energy in atoms. We briefly mentioned energy in molecules when we talk about the MO theory. But now the question becomes, how do we actually measure those energy levels using spectroscopy? Because spectroscopy, you can imagine that as our eye to see the molecules in microscopic setting. And then after talking about each individual energy in a molecule, we'll look at a full picture, which means what is the reality? What is the full spectroscopy picture we have? And depending on the time, we'll see if we have time to go over traditional optical absorption spectroscopy. All right, getting started. First topic, energy and motions of diatomic molecules. So for this point, I want to take some time and quickly go over a review on the Bohr-Oppenheimer approximation. So what the Born-Oppenheimer approximation is saying is that motions of the nuclei and electrons in a molecule can be treated separately. What that means is when we're thinking about a molecule and the movement of the nuclei and the electrons, when we're looking at the nuclei as fixed, we can use that fixed position to solve the electronic Hamiltonian and get an electronic wave function. So the idea here is that electrons are moving way faster comparing to the nuclei. So in the perspective of the electron, because they're moving way faster, they feel the nuclei are fixed. The second part of the Born-Oppenheimer approximation is we're assuming electrons are delocalized potentials. So again, what that means is, judging by the eye of the nuclei, the electron movement is so fast, so they don't feel or they don't see electrons as individual particles. Rather, from the nuclei perspective, they feel the electron as a delocalized potential or delocalized electron density, if you like. With that in hand, we can come to the point in writing out the energies or decomposition of the energies in a diatomic molecule by treating the electronic energy and the motion of the nuclei separately. So here we have 4 different terms. The first term here is electronic energy. So apparently, judging by its name, it's describing the movement and the energy of the electrons. And we spend lots of time talking about electronic energy. But in spectroscopy, we have 3 more terms that's describing the motion of the nuclei. One of them is the vibrational energy, or EVIB. We also have the rotational energy. And at the end, we have the translational energy. And all 3 of them describes motions of the nuclei. So this is just a quick overview, and we'll go over each of the terms here one by one. All right, starting from the electronic energy. So the electronic energy part will be more or less a review, because we already discussed this in our previous talk, especially these are the topics before midterm 1. When we talk about electronic energy, we have 2 types of spectroscopy method we can use. The first one is a photoelectron spectroscopy. So in the photoelectron spectroscopy, what we have is we use a high energy laser beam, and we excite the atom so much that the electron actually get ejected, and we can measure the kinetic energy and derive the ionization energy of that atom. So before we were talking about atom, but photoelectron spectroscopy is equally applicable to molecules. So in typical cases, photoelectron spectroscopy uses X-ray. So let's look at an example here. This is the neon photoelectron spectroscopy we were measuring. So this H mu photon here has photon energy of 1253.6 electron volts. So what's the wavelength of that beam of light is being used? So we can calculate the wavelength of that photon to be hc over E photon. And you can plug in the numbers, or skip the plug-in number part, and do the calculation to get 9.9 times 10 to the negative 10 meters, which is an X-ray. So for this part, if you don't remember where that equation comes from, you can go back and review our lecture note when we talk about photoelectron spectroscopy. The bottom line here, E photon equals to h mu, and then mu equals to c over lambda. We're solving for lambda here. Or, as a take-home message, the photoelectron spectroscopy measures ionization energies. Or what we're exciting, not only the valence electron, but also the core electrons. And typically we use X-ray with wavelengths in region of 3 times 10 to the negative 9 to 3 times 10 to the negative 11. So photoelectron spectroscopy, we're ionizing the molecules. We can not only ionize their valence electrons, but also activate or ionize their core electrons. So that is why photoelectron spectroscopy, we need a high energy laser beam, typically an X-ray. In our previous discussion, it says lecture 4, it should be lecture 5 here. When we talk about Bohr model, we also discussed, well, I believe Dr. Huang discussed atomic absorption and emission spectrum with you. So again, this is what we are having. On the left-hand side, we have the emission spectroscopy. On the right-hand side, we have the absorption spectroscopy. In these experimental setup, they are different. In the emission spectroscopy, you start from excited sample. In the absorption spectroscopy, you start from the unexcited sample, but you have an external light source. But in both cases, in emission and absorption spectrum, we're measuring the relative energy levels of your valence electrons. You're exciting your valence electrons from a lower lying electronic state to your higher lying electron state. Or you start from a higher lying initial state and have the excited sample relax back to the final state. All right, so these parts are, again, a review. If you're familiar with it, great. If you feel this part really strange, I highly recommend you go back and review this section. The take-home message here is, again, we're talking about electronic energy. But using the absorption and emission spectroscopy, what we're having is measuring electronic energy levels. And by, say, electronic energy levels, we're talking about excitation of valence electrons. And since now we're working with valence electrons only, we're leaving the core electrons untouched. We don't need that high energy laser beam. So the typical wavelength we use for absorption or emission spectroscopy is UV vis with wavelengths in between 3 times 10 to the negative 6 to 3 times 10 to the negative 9 meters. You don't have to remember this region. You just need to know where to find it on the electromagnetic spectrum. All right. So far, we're all doing reviews about electronic energy. We spent lots of time talking about it, and this is just a quick refreshment. And now we're moving on to talk about something new. So on top of the electronic energy, right? So electronic energy, we're discussing the electron density, we're discussing the energy levels, electronic energy levels. Now what we're moving to is talking about the motion of the nuclei. When saying motion of the nuclei, in this case, we're just talking about the diatomic scenario. There are three different types of motion, or three different types, fundamental types of motion available. The first one of them is called the vibrational energy. So what does it mean by vibrational energy? So here is a quick illustration. The drawing is not perfect, but you can imagine a chemical bond that's connecting atom A and B. In that diatomic molecule, this molecule can expand or contract like two balls on a spring. So it's not a rigid stick connecting the two atoms. Rather, it's more like a spring. It can compress or it can elongate. So in this process, likewise, we have several properties we can measure. We can measure the bond force constant. Or this is related to the stiffness of a spring, if you may. We can also measure the reduced mass. All right, so now we're talking about the vibrational motion in a chemical bond between two atoms. So on the energy level diagram, what does the vibrational motion looks like? So here is the Morse potential. We've seen the Morse potential when we talk about H2, and here is just a quick illustration that on this Morse potential, depending on your bond length or the average bond length, you can have different level of vibrational energy levels. So in this Morse potential, when we look at the delta E vibrational, what we have is the translation between vibrational state 0 to vibrational state 1. So there are equations associated with that delta E vibration, but for this class, again, it's a surface level introduction. I don't want you to have a very quantitative relationship, but here just know on the Morse potential, you can have different vibrational energy levels. All right, so when we talk about vibrational energy levels, in this case, what we have are excitation of vibrational modes. So since we're only moving between different vibrational modes, where that delta E is actually a relatively small number, so we only need near-infrared light to activate that vibrational motion with lambda in region of 3 times 10 to the negative 4 to 3 times 10 to the negative 6. All right. So let me go back to this Morse potential and just rewind it for a quick moment. So this entire blue curve here is my ground electronic state. So where will my first excited electronic state be? And how do you sketch it on this plot? So my first excited electronic state will also be a curve like this. So on the bottom here, that's my ground electronic state. And here we can have our first excited electronic state. And in my excited electronic state, likewise, you might have different vibrational levels. So this is why I say this delta E vibrational is a very small number, because comparing to the energy difference between different electronic states, this delta E is quite small. We'll see the full picture again soon after. So this part is our vibrational spectroscopy. The second fundamental motion of a diatomic molecule is called a rotational energy. So like the name said, we're talking about rotation of a molecule. So in the rotational of the molecule, when we're describing the rotational mode, now people use the rigid rotator model. What that means is we're assuming, we're not considering that vibrational anymore. We're just assuming there's a stiff stick connecting the two atoms, and they're just rotating in different directions. And by measuring the rotational spectroscopy, we can get information about bond length and bond angles. So the rotational energy levels are even smaller, requires even smaller excitation comparing to the vibrational energy. So we only need microwave or far infrared. For rotational spectroscopy. The last molecular motion we have in mind is called the translational energy. So typically, photons in spectroscopy don't have enough energy to actually disturb the movement of the molecule. So for this class, you just need to know translational energy is part of the game. So we don't typically measure translational energy using photon spectroscopy. So what is the full picture of all these energy levels in spectroscopy? So this is the full picture. It is a little bit small, so let's think about it. So what does it mean? First of all, we can have different electronic states. So each of that curve is an electronic state. And within that electronic state, you have multiple levels of vibrational states. So mu here, I know it's confusing. We use mu to identify different vibrational states in spectroscopy. So, quick question here. If we're talking about an excitation for a ground state molecule from the ground state vibrational motion to the second excited vibrational motion, where should I draw that arrow? It's ground state electronic, and then we want to excite it from the ground vibrational state to the second excited vibrational motion. So the arrow we're talking about is from here to here. All right. And within these vibrational states, within those highlighted gray states, if I zoom it out to look at the rotational energy or the rotational state, so here the rotational states are denoted by J. You can have different rotational states within each vibrational state. Yes? So if you think about it, here we're zooming out this highlighted gray part to the rotational state. So they will naturally come from the ground electronic state. But if I highlight this part, then that's going to come from the first excited electronic state. So what I expect you to do is, first of all, know what each spectral region means and why do we need higher energy to get information about electronic state and lower energy laser beam to get information about the rotational state. Like, how do they organize? Secondly, if I give you a random question like, can you tell me how to go from the ground rotational state to the, say, second excited rotational state? How to draw that arrow? What's the arrow between the ground electronic state to the first excited electronic state? So know how to draw those arrows and how to read that sentence. All right, I'll pause here to see if we have questions before we move on. Yes. Right, so the question is, does each excited state have its own curve? So the quick answer is yes. When we talk about electronic state, it may not always look like this. At the higher energy, your electronic state might have something of this shape. The shape might be different, but each electronic state can have a different curve. Yes? So that's that point here. This one is not frequency. Again, I know it's confusing, but in spectroscopy, people use this symbol to derive this is the first state for my vibrational energy state. This is a ground vibrational energy state. Mu equals to 1 means that's my first excited vibrational state. Don't confuse it with frequency. Next. Yes. Sorry, what's the question again? So what I want you to know is when we talk about vibrational energy, you need to know what the range of that vibrational energy is. We don't need an X-ray to observe vibrational energy. You only need an IR spectroscopy to look at vibrational energy. Or if you want to get information about electronic energy, you should be using something that's higher, like UV vis, to get information about electronic energy. So again, for this class, it's just a quick introduction. I want you to get an idea about what kind of spectral region to use if I want some kind of information from the spectroscopy, like rotational mode. We're getting information about bond length and bond angle, and we only need something like far infrared. All right, and let's do some examples together and see how do we use or how do we solve spectroscopy problems. First example here is a young chemist wants to do spectroscopy analysis of HCl. Which EM radiation should we use? For that part, we're given some information. Like say I'm telling you the delta E electronic, let's say the delta E electronic energy between ground state to the first excited state of HCl is about 9.5 electron volts. First thing, what does that electronic energy mean on this diagram? So it's an electronic energy. So what we have is we're moving from the ground state electronic curve to the first excited electronic curve. So here, this is what our delta E means on this diagram. And the question asks, which type of EM radiation should we use? So we can do that calculation together. We know that delta E HCl equals to 9.5 electron volts. And my lambda electronic, again, equals to HC over delta E. You can plug in the numbers to get 1.306 times 10 to the negative 7 meter. And this wavelength, if we look at the electromagnetic spectrum, you can see that's UV light. So that's the electronic, how to translate the energy back into wavelengths and identify the spectral region of that wavelength. Next up, moving to the vibrational case. So here, again, it's given the delta E vibrational of the same molecule from mu equals to 0 to mu equals to 1. And here the delta E is given in wave number. We'll talk about wave number soon. So what is that vibrational energy on the diagram here? It's from mu equals to 1 to mu equals to 0 to mu equals to 1. So that's my vibrational energy. Delta E vibe. So, wave number. How do we translate that wave number? So Cm minus, or wave number, that's a unit of energy in spectroscopy that people use a lot. What it means is just one wave number is equivalent to, say, the frequency is 30 times 10 to the 9 hertz. So in here, when we say the delta E vibrational equals to 2990 wave number, that is equivalent to, say, the frequency of this vibrational mode is 2990 times 30 times 10 to the 9 hertz. If we do that calculation, that's 8.97 times 10 to the 13 hertz. And then you can easily translate that back to wavelengths. That's just C equals to mu. Gives you 3.34 times 10 to the negative 6 meter. So this is near infrared. All right, that's the vibrational. So again, what I expect you to do is, if I give you this kind of information, say what my delta E vibrational is, can you first label that delta E on the diagram that's given, and then tell me what kind of laser you should be using in order to excite that specific motion. One last example here, the rotational barrier. So let's just say, given the delta E rotational, again in HCl, but now we're talking about J equals to 2 to J equals to 3. So we're talking about here. And now the wave number is only 62. So the frequency rotational equals to 62 times 30 times 10 to the 9th hertz, or 1.86 times 10 to the 12 hertz. The lambda rotation wavelength equals to C over frequency. It's about 1.61 times 10 to the negative 4. So it's a relatively long wavelength. So this is in my far infrared or microwave region. All right, so these are some of the examples we did. Again, it's relatively surface level, but know what it means by each delta E, how to label them on a diagram, and how to translate the wave number to the actual spectral region and tell us what kind of laser we should be using. All right, and here is a quick summary table on all the spectral region we discussed. Again, when we have radio wave, that's a nuclear spin. We'll talk about that in our next lecture when we talk about NMR, the nuclear magnetic resonance spectroscopy. And then rotational excitation, we use microwave or far infrared laser. Vibrational, we use near infrared. And then electronic, for valence electrons, we use visible light or ultraviolet. The core electronic energy, we would need X-ray. Just a quick summary. Different type of spectroscopy will give you different molecular information. That said, again, spectroscopy is just our eye in a microscopic world. We use spectroscopy to depict what those energy levels are in different molecules. The real world is actually more complicated than it looks like here. For example, the vibrational mode and the rotational mode can overlap with each other. Say if you're using the near-infrared laser to activate those vibrational mode, you're at the same time activating those rotational modes, and they can overlap with your spectrum. But that's too complicated. We'll save that for you in your future lectures. Okay, any questions before we move on to traditional optical spectroscopy? Okay, that's good. Okay, next up, traditional optical absorption spectroscopy. So again, typically speaking, in absorption spectroscopy, what we're seeing is a molecule at ground state, or in this case, I'm denoting the ground state as E1, can absorb energy from photons and get to an excited state, E2 or E3. So in the typical setup of an absorption spectroscopy, what we have is we can have a light source. We also see this when we talk about coloring transition metal complexes. This is just a zoom-out version. You have a light source with some type of h mu. So mu is the frequency of the light with the initial intensity I0. So when that light source passes through your sample cell containing molecule of interest, when the frequency is matched up with the energy required for that excitation to take place, the light can get absorbed and then will leave with a smaller intensity. So when we look at what we have on my acceptor, typically is when the frequency of absorption is taking place. So here I'm saying mu21, mu31. So here mu is back to frequency. So mu21, what it means is from energy level 1 to 2, that's the first absorption that's taking place. Mu31, that's from 1 to 3, that's where the absorption is taking place. So whenever an absorption is taking place, that intensity of light drop, because the photons are being used in exciting the sample molecules from a lower state to a higher state. So, okay. I'm running a little bit faster than I expected, which is interesting, but okay. In the traditional optical absorption spectroscopy, here's a quick setup. What we have is we're talking about a sample in a solution cuvette. So likewise, we'll use the same light source, but we need to exclude the effect of the solvent. So in the typical setup, you will have the light source going into two different directions. On the top, you have the sample solution with your sample molecule or your molecule of interest and goes to your detector. At the same time, you also have a reference cell with only the solvent. So by taking the difference of those two absorption spectroscopy, we can get the effect of the sample only. So there are several factors that's contributing to the amount of light that's being absorbed by the sample. First thing is the concentration of the light that's absorbing, typically on the sample, or my red dot, my solute. and also the distance of light that traveled in that cell or in that cuvette or in that container. Yes. So IP here, just say the intensity after passing through that sample. I0 here is the intensity of that reference cell. So that boils down to the use of Beer's law, which I see people smiling. So if you take AP chemistry, you probably see that before. A here, that's the absorbance or optical density. That equals to logarithm of I0 over IT. So these two are the measured quantity in the experiments. And these properties are dependent on three different things. The epsilon here, that's the molar absorption coefficient. Or you can think about that as a constant you can search for. And then C here, that's the concentration of the sample. And L here, that's the path length, or what's the size of your cell, of your cuvette that's containing that solvent. The traditional optical absorption spectroscopy, we use that a lot to measure the concentration of a solution. So by, say, measuring the concentration, you can easily imagine that connect to stoichiometry problems. I'll see an example question here together. So the question is, say, imagine you have a solution of tryptophan with an absorption peak at A equals to 0.60 at 280 nanometer in a 1 centimeter length cuvette. And we're given epsilon equals to 6.4 times 10 to the 3. And can you calculate the concentration of tryptophan in this sample cell? So the equation we want to use, again, is Beer's law, which is A absorbance equals to epsilon times concentration times length. Or since the question is asking for the concentration, we have C equals to A over epsilon and L. Plugging the numbers, we have C equals to 0.60 over the epsilon which is given, 6.4 times 10 to the 3 times length, which is 1.0 centimeter. And know that here in both cases we're in centimeter. Just keep in mind of that unit. Do that calculation, we get the concentration to be 9.4 times 10 to the negative 5 milliliter. Or this is molar, if you may. All right, so that's the traditional optical spectroscopy and its application in determining concentration of a given solution. The last topic here is again color. So this is again related to our transition metal complexes topic. It's when we talk about color and also the maximum absorption wavelengths. So in a solution, when the molecules are absorbing a certain color, what we see are their complementary colors. So this is more or less a review. If we're talking about if a molecule absorbs yellow color, what we see is its complementary color, which is purple. We did that with our chromium complex. Likewise, imagine if a molecule absorbs blue, wavelength would the color of that solution be? So blue color is being absorbed. So what we see that's to be an orange color. So we always see it's complementary color. All right. So I'm going extremely fast today because I managed to finish not only what we planned, but also the first topic of our next lecture. I guess I left a quick question here to work on. It's in what wavelength range do you expect to find the maximum in the absorption spectrum of the dye Prussian blue? So it's a blue color. What we have expect, go back to this wheel of color. We expect it to absorb orange color, so it gives you that bright blue. And this orange light, you can go back to the spectral, electromagnetic spectral region and find that wavelength range. Okay, that's all I have for today. We'll see if you have questions. I'll stay outside for questions. And I do have my last office hour from 10 to noon today. If you want to stop by, I'll be in my office.